Good afternoon, everyone. I am not Vineet Jain. He was the person who was supposed to initially present. My name is Tarique Shakil. In fact, me and Vineet Jain worked together 5 years in the ACTS routing protocols team. We also authored a book together on Lisp. So he thought, he just threw me in. So I'm glad to be here. I'm very passionate about BGP. Been working with BGP for 15 years across different environments. I've been 11 and a half years in Cisco. So I started with service provider, 5 years, moving to enterprise routing and switching, 2 years doing delivery. And for the last 6.5 years, I've been working in the data center business unit with ACI, VXLAN, BGP, VPN. And with large-scale data centers, BGP also has a huge role, right? In fact, I encourage every data center engineer who's used to layer 2 world, you must learn BGP. It is here to stay, right? Today's agenda, we have a 45-minute session, and as we all know, you can't really learn troubleshooting BGP in 45 minutes, right? So I'm going to completely focus on one area of BGP, which is updates. That's it. We're just going to talk about what are the different kind of issues that we can face with BGP updates. There are many other slides in there that you'll see. I've hidden them, but that's just for your reference. There's a whole section on NXOS. I don't have time to cover it, right? But I do want to focus on concepts, approaches, command, and show you examples across the various platforms on just troubleshooting BGP updates. Is that fair? Right? So at least when we go outside, today you'll have some approaches and ideas how to address troubleshooting update issues in a BGP, large-scale BGP fabric. Sorry, I keep on saying fabric, network, right? Sorry, the data center guy in me. So let's look at a quick revision of BGP update processing. In the middle, we have the BGP table. The RFC term for that is local RIB, right? Local RIB is what? The table that the BGP speaker, the router, uses to store all the routes that it receives, right? And the routes that the operator of that router will inject inside manually. What are the ways to install routes in the BGP table by the operator? First, we can do it through the network statement, right? The network statement, what does it do? It essentially allows you to inject any route that's in the local routing table of the router inside the BGP table. Then we have redistribution. Redistribution, the common mistake people make with network statement is what? They don't match the mask that is available that is matched to that is existing in the routing table. Then we have redistribution. You're redistributing any other source protocol, OSPF, ISIS, EIGRP. I have not worked with the EIGRP for 9-10 years, but I'm sure some of you may have, right? When we're redistributing from any of that source protocol into BGP, what are we doing? We are taking different metrics, right? And that is available in the different protocol, and then we have to somehow map it into the BGP, and usually MED is used for that, right? Multi-exit discriminator. Now, one thing you need to keep in mind is that the default routes that are learned by those sources of the protocols are not injected in the BGP table. And the other things you must keep in mind are things like, for example, in OSPF, when you redistribute OSPF into BGP, external routes that are learned in OSPF are by default not redistributed, right? So these little things you need to keep in mind. I'll give you a few examples later. So that's the second method. Then we have aggregate route. Aggregation is what? You're summarizing. You have longer prefixes, you're summarizing into smaller prefix length and advertising it out. That is also injected in the BGP table. Then we have default information originate. That's BGP advertising a default route to its peers, but there's a condition involved there that the default route must already exist in the routing table. Now what we see here is that that's us, the operator, installing routes into the BGP RIB, but the BGP router will also learn routes from its peers. And when it learns routes from its peers, it will first go to the inbound policy. That's some sort of filter that we use to control what goes inside my BGP table, right? And we'll see some of those issues that may happen, some common mistakes people make there. So these are updates being received by the local BGP router. Then what happens? The BGP table then goes to the best path decision criteria here, logic, and calculates its best path, and it will only install offer the best path as a candidate route to the routing table, right? And then the routing table will do its logic of, hey, who has a lower AD, and then we'll install into the routing table. Then The best path will also be advertised to the BGP peer, to its peers. And it will advertise it, if there's an outbound policy applied in the outbound direction, it will go through those filters and be advertised to the peer. So this is the whole story of how updates are installed on the table, how updates are received, and where filtering is applied, inbound and outbound. I think this is a quick revision. Any questions? Okay. So let's start this conversation by looking at a problem, a common problem that attack engineer will see or you may see in your network. Right, so a lot of the way I've approached this lesson is examples and concepts. So there's no theory slides, right? No theory slides. Example, explain the concept, how it's working, why did it fail, how do we rectify it. So in this example, we have an output of show IP BGP summary begin neighbor. So show IP BGP summary command in iOS tells us the neighbor state, peer state information. And what we see here is that this particular neighbor, 1.1.1, is the peering has been flapping, right? The peering has been flapping. And we see that by the up-down state. It's only been like 1 minute, 20 seconds, or 2 minutes, 24 seconds. And now the interesting thing here is the output queue, right? Now every software system, the routing system will always have messages that it gets and messages it sends out. We have queues for those, software queues. And BGP being a TCP-based protocol, TCP is what? A socket connection, right? Between one router to the other router. And as we know, TCP provides reliable delivery, right? And it keeps track of all that window size, receive window, and things like that. So now here you'll see that in the output queue, we have 97 packets. I'm sending messages to be sent out to this particular neighbor, but I'm noticing that the output queue packet count is increasing, right? So that means, but my message sent count is not. It's remaining at 284. What is this telling me? This is telling me that this local router, while trying to send updates out, is not able to, it's not leaving the router even. It's getting stuck in some sort of queue, outbound. And what kind of impact can that have? For example, keep alives can even go in those queues. Update messages can even go in those queues. Now, if keep alive is not being able to send out this router, and the peering router is not receiving those keep alive, what will the peering router do? It will drop the session. Right? So a lot of times, these basic update choke points or issues in generating updates have a domino effect even in keep alives. And this is a very common thing that you'll see. The next type of scenarios we'll look at with regarding updates is missing routes and stale routes. So missing routes are routes that we do not receive. We do not get from our neighbors. And there are multiple reasons that may happen. One of the reasons may happen is that there's some sort of filtering, inbound and outbound, right? And we know in BGP, it's like a Swiss Army knife. They've given you so many different types of filters, right? Prefix list, AS-path filters, route maps, access list, you name it, right? There's so many ways and so many approaches that communities that we can use to control the routes that we receive and the routes that we send out. They could also be issues with the BGP process itself in generating updates and processing updates. For example, even the resources utilized by the local system, if the memory is high, the CPU is high, we'll look at a couple of examples of those. So the missing routes is, okay, I'm not receiving it. Stale routes is, whatever information I have, I may be having information that shouldn't exist. So that, for example, a remote network went down, the remote router generated the update, but I didn't receive the update, and therefore I still have old information. So it's not, basically there was some sort of convergence problem. Or I do have information about that network, but it's not accurate. What do I mean by that? The next hop, or the MPLS, the outbound MPLS label is not the updated one. So that's a stale entry. And what will that cause? Hey, if my next hop is not valid, what's gonna happen? You're gonna end up black holing traffic, dropping it, right? So I wanted to define these things, missing route and stale routes, and how do we analyze them. So let's look at missing routes first, right? That's a bit of a simpler example to look at. So if we look at this example, this is from iOS XR. So I'm sorry I have to jump between platforms because I'm trying to satisfy everyone's service provider, data center, and XOS. So we'll be jumping between it. But don't worry, there are basic examples to help get the concepts across. So if you see here, in iOS XR, there's one thing you must remember. Anytime you form an eBGP peering, you have to have an outbound or inbound policy, or else the peering, no routes are advertised. Now, remember, if those of you who've worked with NXOS or iOS or iOS XE, what happens when you issue neighbor command, whether it's an iBGP or eBGP neighbor, it doesn't matter, right? The peering comes up as long as the network connectivity is there. In iOS XR, you may even be able to ping the neighbor, but the peering will not come up. Why? It demands, for eBGP neighbors, a route map, and people forget that, those who are new to iOS XR. So here I've just created a simple route map, which basically says if destination A1 prefix set is the iOS XR term for prefix list in iOS. Same thing, same function, right? And we use something called RPL, Route Policy Language. So it's the fancy way of saying a route map in iOS XR. And you'll see that if the route exists in this prefix list, pass, else drop. And then I'm simply going into the BGP routing process under the neighbor group, IGW, remote AS, address only IPv4, and I'm just applying a policy inbound. That ensures now that this local router will receive routes inbound, and it will be filtered based on this route map. If this route policy was not there, for some reason, this iOS XR router will not receive any routes from its neighbor. So always remember that, right? So you need one inbound and outbound, by the way, both. So inbound just controls what you're going to receive. Outbound, so if this local router wants to send outbound, you need an outbound policy too, for eBGP neighbors only. So this is a basic example from iOS XR platform. Now let's look at another example. Now, a little bit of review. So when two BGP peers come up for the first time, they send an open message, right? Open message says, hey, hello, I am router ID this, my AS number is this, right? And, here's my password, right? And I want to start opening a peering session with you, right? So then, remember, in that moment that happens, BGP starts sending all its update, right? BGP, when the peering comes up for the first time, it sends up all its update. So what happens is the receiver router goes into what we call read-only mode, which means like, okay, I'm waiting for you to send me the updates. Keep sending me the updates, okay? And when you're done sending me the updates, signal to me. Signal to me. So how does a router signal? The sending router will signal either by sending a keep alive or a EOR notification. EOR means end of row, which means that, hey, I've finished sending you my BGP table, okay? This is all the update I have for you. A lot of times what happens is that people with very, you may be in a situation where you're noticing the routes aren't being received, like why I'm not seeing the routes. You need to verify the BGP process to see, is it stuck in read-only state? Or is it still receiving updates, right? And now there can be multiple conditions that can cause the router to be in this state. It may be very busy, it may be very slow. The link itself, the transmitting link itself may be slow in transmitting, or maybe even the BGP MSS value, maximum segment size value, right? Which is the size of each update that is negotiated between two BGP peers. By default, you use 536 bytes if you don't define it. What happens if you have a massive update? It's going to be sending lots of packets, right? Lots of packets, and that takes longer for the BGP system to converge. So how do you check if your BGP router is still in the process of receiving updates or in read-only mode? You can do show BGP command or show BGP process performance statistics details. This will tell you if your BGP process is still in read-only state, okay? Because it will only start calculating the best path after it exits the read-only state. And this is per peer. Okay, here's a very basic example I'd like to engage you guys on. Unexpected routes are appearing, okay? So let's try to understand this route map first. So we have a route map here. Its name is OSPF2 BGP permit 10, match IP address prefix list filter v4, okay? And we're redistributing OSPF, but we're matching it, filtering it with a route map, OSPF2 BGP. What is the outcome of the above redistribution? What happens? Anyone want to take a guess, or anyone want to share your thoughts? Yeah.
He's going to redistribute the OSPF1 process, but it's going to filter it via that prefix list. There's an ACL called filter v4.
Yep.
With a list of stuff that it's going to filter. The subnets keyword is missing, right? So it won't get smaller prefixes.
Yes, that's a good point. And there's another point here that we didn't do match external. So if you wanted to redistribute external, but there's another point. You notice that this route map doesn't have any other statement after it. So what implies? Right? There's an implicit denial. So that means that you may have implicitly denied many other prefixes which you didn't intend to, right? For any reason. So this is a common mistake people make, right? This is a very common mistake people make. And very basic example, but you see this. So now I'll take it a bit, elevate the complexity just a little bit more. And this one is a bit tricky. And by the way, I probably spent like 2-3 hours troubleshooting this scenario once. And it was really embarrassing, right? But okay, let's understand the route map first. So OSPF2 BGP permit 10, match IP. The key thing to notice is the address family. This is matching IPv4. This is matching IPv6, right? And then, of course, there's going to be implicit deny after that, right? Because we didn't put a route map permit blank state match state. So then we go in, under address family IPv4, redistribute OSPF1, route map OSPF2 BGP. Now, you notice here, this is for address family IPv4. Now, when we're redistributing this OSPF1 into BGP, address family IPv4, it's referring to this route map. The route map says, okay, I'm going to match IP prefix list filter v4. Hey, this is for address family v4. It'll match. It'll redistribute the routes. But then when it gets to the next statement, remember, route map goes, it's not an ACL, right? ACL, you finish ones, you match an entry, you don't proceed to the next entry. Route map will go in sequence. What happens when it goes to the next sequence? Match IPv6. Wait, so what happens is that the Cisco router actually interprets that as a blank match statement. So what happens? This becomes equivalent to a route map OSPF2 BGP permit 20 with a blank statement. Because this is under address family IPv4, but this is IPv6. So what happens? Unintentionally, we permit everything. So this is a problem that a lot of people do. So what's the lesson learned here? Separate your route maps based on address family. Don't mix them. Don't mix them, right? So everyone understood this one, right? Yeah, I mean, I spent 3-4 hours trying to figure this one out once. And then later I was like, oh, God. Okay, so this is a summary of what I already explained, so I'm not going to, okay? All right, now filtering. Okay, this filtering, we all know that we need to use, routing tables get very large, so we need some way to keep track of them and analyze the BGP table. And regular expressions become our friends, regex for short. I'm not going to go over all these, but some of them are very common, right? Like underscore means to match a space. Caret means what? Start of the string. $sign means end of the string. So let's just go straight to the 2 examples. I have put more examples in the slides for your reference, but I'm just going to go over 2 for now. So if you see this example, show BGP IPv4 unicast, regular expression, underscore 300, underscore. That means what? If I were to translate that to English, how would you interpret that? Yeah, anything that went through AS300. Okay, 25 minutes. Okay. Anything that went through AS300. So you see here, every entry here has AS300 in it or transited through AS300. All right, that's a simple one. Now, one thing you guys must keep in mind, when you're looking at an AS path, you always read it left to right. Okay, so for this example, remember caret sign is beginning, right? Remember the caret sign indicates the start of a string. The string that we're referring to is what? The AS path string here. So we read it from left to right. So here it's saying it starts with 300 and anything after that. So you notice that every single one starts with 300. And when you look at this, starting with 300 means what? The pure AS that you receive the route from, right? The pure AS that you receive the route from. So these are the most basic ones. I have a couple other fancy ones in there, but they're in the hidden slides, but you'll get a copy of it when you download it. Now, how do you troubleshoot this now? Okay, I get it. These are the kind of problems that I face with filtering. How do I actually troubleshoot them? We run debugs, right? These are general debugs. Here's an example from iOS XE, where we run a debug, BGP IPv4 unicast update in, right? And we can do soft in or in, right? Now, anyone know the difference between soft in and in? Soft in refers to soft reconfiguration, right? So now BGP has 3 databases. I talked to you about the local RIB, which is the traditional BGP table we always talk about. But BGP also has 2 other databases, which is the adjacency in and adjacency out. Adjacency in is the BGP database that stores every BGP update that a router gets from its peers. It's the unmodified, unaltered, the original format update that it receives from its peer. Then what does it do? It puts the policy inbound, then imports it into its BGP table. So when you do soft in reconfiguration, it's actually, what it does is that every BGP update a router receives from its peer, it stores it in that database. What does that do? Multiply your memory requirements, right? But what is helpful in doing? Every time you want to see the original update that you received from the neighbor before you apply the filter, you can see its original format. Then you can see, is my filter actually applied, right? But that was the old way of doing it. Now we have better ways of doing it called route refresh. Route refresh essentially says, hey, neighbor, send me your update again. It signals it to it, so you don't need to store it locally, right? So I just want to explain that. But here you see that from this debug that a specific prefix is being rejected by the filter. And this is a command from NXOS, but it's for the same purpose, right? Here you're validating that, yes, a particular prefix got dropped because of a filter applied to it. Filter rejected it. Here's an example from iOS XR. Again, the structure, right, is here we have an RPL, R4 in. If destination is in any network that starts with 10 with a prefix length less than 32, then pass. Then it has another condition. So you notice here we applied this policy inbound to this neighbor, 10, 1, 45, 4, and it went through it tried to match both conditions, and it says, oh, the specific prefix didn't match this condition, neither did it match this condition, end policy result drop. So moving on to stale routes, okay, again, stale routes, I explained to you the causes, right? I explained to you what it exactly means. Let's look at an interesting example. A few things to remember here, though, is that stale entries can exist at multiple layers, right? A lot of books won't talk about this. A lot of the books will focus purely on the control plane layer, right? So a lot of times what happens is that even your data plane layer may have stale entries. So what I mean by that is what? The router received the latest updates in the control plane. The BGP table looks good. It's matching, it's converged, but the programming between the control plane and the data plane is not in sync. That's also an example of stale entry, but where? In the hardware. And that's a common issue that you'll experience too, but I don't talk about that. Your TAC engineer will take care of that, okay? So you don't have to worry about that, right? Because at that level, you're looking at how the forwarding adjacency information is programmed at the TCAM level, right? But it's not that hard, to be honest with you, right? But we don't talk about that right now. But here, let's look at this example. This is an example from MPLS, right? And so here we have a PE router, okay? I just want to go over the diagram, then we'll go over the show commands. So this PE router's loopback is 10, 229, 37, 92. It's advertising its loopback to these route reflectors, right? We have an IGP MPLS BGP network here, right? Then these route reflectors, we have a hierarchical route reflectors design. These route reflectors advertise to this central route reflector using BGP labeled unicast. Okay? So that means basically BGP is advertising its route, but then it attaches a label with it, right? BGP is also an MPLS protocol. It allocates labels too, like LDP, like RSVP. Okay, so now moving on to, so we look at the route reflector. This IP is 10.29.34.128. Let me go to the front slide. So let's try to understand. Oh God, why are you jumping so much? Sorry. Okay, I have to be gentle with it. Okay. So this is the BGP table for address family labeled unicast for this entry for the loopback of PE1. So if I go back to the diagram, I'm on RR2. RR2 is the lower route reflector. Okay, I'm looking in the BGP table of this route reflector for the entry for this loopback IP. The local label, all right, the local label is the label that this RR2 is going to advertise to its neighbors. The receive label, which is 26,596, is the label that this RR2 received from RR1. How do I know that? Because I have RR1's router ID here. If I go back, 3792, wait, sorry, it's not RR1's router ID, it's this one. 10.29.34.128, the next top router is 10.29.34.128. So mark these, okay? So this is the local label, 2528. This is the one that RR2 would be advertising to the central RR, okay? The local label of RR2 is what it's going to advertise to central RR. When I hop over to the central RR, which now I'm on the central RR, for the entry for the PE1 loopback, you notice that the outbound label is 27.183, which it received from 10.29.37.2. 10.27.37.2 is RR2. So which means what? The local label that RR2 is advertising to the central router does not match. That is an example of stale entry. Right? This is 27,183, while the local label advertises 2528. This is an actual customer example. I just obfuscated the IPs, right? So stale routes, how do we troubleshoot it? Okay, you should give me a couple of examples. In iOS, to be honest with you, it's quite difficult without doing debugs, right? At least at the control plane level, you will have to run some sort of conditional debugs. I'll show you how to do that the safe way. And you wait for the problem statement, for the symptom to show up, and you try to run debugs to understand why the stale entry, why the updates did not occur properly in the BGP table. While iOS XR and NXOS, they have what we call traces. There are logs. They're very detailed logs that are stored in memory. You can control the size of that memory to small, medium, large, right? And they are extremely useful to debugging and understanding why a particular route entry was not updated properly in the local table. And so these are very common commands that you can run on iOS XR or NXOS to troubleshoot any sort of stale entry. Now, debug commands, as you know, can get dangerous, right? Depending on the size of the table, right? So if you know the specific routing entry, like in the previous example, I knew exactly which network, which prefix I cared about, I can use what we call conditional debugs. The conditional debugs, what it does is that it will filter what it will show in the debug command. And here you see in the iOS example, I created an access list where I'm permitting 10.1.0. The wildcard is 00255. So that means what? I'm matching the first 3 octets. I only care about the 10.1.1.0, and I'm using that ACL and referring to that ACL in my debug to this specific neighbor. 2.2.2.2. Right? So that really narrows down what you're going to see in your debug instead of an entire screen of updates. Right? You're focused on the specific neighbor and the specific prefix. And the same thing, but here's an example with iOS XR for a different prefix, right? But it's doing the same thing, right? We're referring to a prefix set. Prefix set in iOS XR is equivalent to a prefix list in iOS and iOS XE, right? And same thing, debug BGP, update IPv4 unicast in out route policy debug BGP. We're referring to the route map that we created here. This is what we call conditional debugging. right? There's a lot of other things, best practices you could do, like you can even create a file, a debug file, give it a name, and all the debugs will go to that file. You can define the file size. So all the TAC engineers, when they're troubleshooting real time on your systems, this is the kind of best practice that they try to follow. It's well documented. You can see it in a lot of the Cisco community forums. Okay, that was for BGP updates. Am I going too fast? Sorry, the pace is okay? All right. So BGP route churn and troubleshooting. So churn and flapping. Let's try to understand a bit of those. So route churn, the first thing, route churns is when your BGP table is constantly updating. It's constantly updating, and one of the symptoms that you'll see, especially in large-scale routing networks, is that the CPU starts to spike. Now, BGP is a complex protocol. It has multiple processes working together. And different operating systems have different names for those processes. One thing you have to remember with iOS, it's what we call a monolithic operating system, which means that it's like one big file. And if any process crashes, the whole operating system crashes, right? But now, of course, with iOS XE, NXOS, iOS XR, these are distributed operating systems. We have threads and processes running independently. You can restart the BGP. The BGP can crash and your router won't crash. So, right, we're in a better spot now for the last 10 years. But now, when the CPU goes high, the first thing you should actually ask yourself, is this an intermittent issue? You know, is this a transient issue? Is this expected? Maybe you are receiving a large update and BGP router process in iOS is the process that does the update calculation and all that. Okay, maybe it's going through a convergence. Let me give it 1, 2, 3, 4 minutes and see if it goes back down. Check your CPU process history, right? And this is exactly what they're showing here. You can do show process CPU sorted. That shows your top 10 processes that are consuming the most CPU. Look at it. And you can also do show process CPU history. It shows your trend. Okay, last 72 hours, everything was okay. It just spiked up right now. I noticed that one peer just came up. Okay, maybe it's reconverging. So that's what you need to, or maybe the router just booted up, right? So narrow down, is this an actual transient issue or is this a persistent issue, right? So now if you think that it's a persistent issue, we'll start analyzing a bit more. So now when you do have a high CPU due to BGP router process, one thing you should also need to now confirm, okay, I have high CPU. Is there actually a lot of activity and updates coming through? How do I check that? In BGP, we have something called table version number. It's like, you know, it's keeping track of as more updates come in, the version number increments, right? As more BGP messages are coming in, version number increments. So here I'm outlining a particular way to understand and scope that problem. So, okay, I'm going to look at the BGP summary, and I'm going to note my table version number, right? The local I'll show you examples. Then what you do, you wait a bit longer, and then you see, okay, did my table version number increment by a lot? Because that indicates a lot of updates are coming through, right? But now, it's all relative now, right? Because, I mean, if I have 150,000 routes, and my table version number just increased by 200-300, that's expected, right? In such a large-scale network with 150,000 routes, you're expected networks will go up and down and, right, updates will happen. This is something common. Okay, but if you notice that the table version number increased by 20K, 30K in terms of value, okay, there's some real, fluctuation happening. Okay, this indicates some form of instability a bit in the network, and that means, okay, we need to look into this. And if you keep noticing that the table version keeps incrementing, and it's not stabilizing, okay, that means that my BGP continuously is reconverging. I need to look into this. It's churning. So here we see an example, show IP BGP all summary. It has this value. It went over 1,800 prefixes flapped, and then it went up, right? We can see another indicator of churn in your network is the routing table itself. In Cisco routers, it keeps track of how long a routing entry has been in the routing table, right, by that, with the timer value. And if you're continuously seeing routes coming with 0, that means what? These routes are continuously being placed into the routing table, and that means there is churn happening. These are symptoms that you can see. So what causes churns, right? So we can see the things like link flaps, things like updates not coming across. For example, I may have a transport network in the middle. I've seen these scenarios. We have two routers. The customer calls me and says, hey, they're directly connected. There's a layer 2 switch in the middle. That's all it is. Like, I don't understand what's going on. Why is it keeps flapping, right? So what happened was that it could even be an optical repeater in the middle that has an MTU value setting. So what happens is that if you have two routers, router 1, router 2, and their interfaces are configured for, let's say, 9,120 bytes, right? MTU size. That's common now with Ethernet, right? 10 gig, whatever, right? In the middle, we have a layer 1 device, right? That has an MTU of 1,500. We're sending 200,000 routes. Let's say there's an internet exchange point or peering between two large autonomous systems. When it sends an update packet, it gets dropped. It gets dropped in the middle, and then what happens? Eventually, the peering will be dropped also, because updates are even treated like keep alives in BGP. Yeah, no, but imagine, okay, that's a very good point you brought up. The question was, hey, doesn't BGP negotiate PMTDU, right? The MTU discovery. Let's say that the transport in the middle disabled ICMP, then that won't work, which is very common, right? We disable ICMP, now you can't do path MTU discovery. So what's BGP going to fall back to? The MTU of the outbound interface, which in my case was 9,120. Boom, right? No updates go across, and you're going to start getting churns. So here's another example with VRF entries, right? Show IP VRF route. Same fundamental principles here, just different address family. And here we're dealing with VPNs. Now, one thing interesting to see is you can actually, let me just go straight to the example, it will be better. So here, how do I analyze the routes that were introduced over time? Right, that's the thing. Like, I want to see the delta. I want to see the differentiation, right? So the way to do that is that you notice when I do the show BGP command, recent 6, my current version of the BGP is 12. This is an iOS command, by the way, right? And so what this is saying is from 6 to 12, show me all of the routes that it's a union. If you look at set theory, it's a union of 6, 7, 8, 9, 10, 11, 12. And it shows it. So you can analyze and troubleshoot 7 through 12 what happened. Your current version is what? 12 here. This is the previous version. So it shows from the range 6 to 12. Now, iOS XR is a little bit better because it actually shows you for every entry what's the version. So when I'm in this command, what I'm doing, show BGP IPv4 unicast version 5 to 7, it's a union version. I want to show all the entries that were there in version 5 of my table, version 6 of my table, and version 7 of my table. And you can actually see which entries are in which version. iOS doesn't provide that. It doesn't give that classification, unfortunately. But iOS XR, this is an XR1, it gives that. So how does that help? You can see over time what route is being introduced again and removed and added, etc. This is a scenario that I have actually hit. So what happened is I had a provider which is known to be largely version 4. This is like 2010, right? A while ago. So this provider was starting to introduce V6. And so I was troubleshooting, they were having a lot of churns and issues, and high CPU, in fact. And I noticed that the V4, everything was okay. So then what I did is that we actually went to verify the TCP socket connection of the BGP session. I noticed, hey, I am seeing rapid increases in messaging in the TCP socket. So there is a lot of activity in BGP, but I assumed the entire time, because when I looked at the show run, I saw like 50 BGP IPv4 neighbors, but there was like 2 IPv6 neighbors way in the bottom that I missed, right, for VPN v6 services that they were just introducing. And they actually introduced like thousands of routes in that v6 in one shot. They onboarded a new tenant that brought in thousands of v6 routes, and for some reason I skipped it at that moment. And then that's when I realized that, okay, you know what? You need to start checking which address families are enabled, right? Because every time you enable an address family, what are you doing? You're bringing in more routes. You're bringing in more attributes. Look at IPv6 by itself. Look at the addressing space. That's going to take up memory, right? On all those things. You're going to have route targets, route distinguishers. Every attribute you add on a route, that's more work for the router when analyzing the best path. So always verify what are the attributes that you're going to always verify all the services that the customer is running, because that's multi-protocol BGP is like a Swiss army of all routing protocols, right? I mean, how many address families do we have? 29? I think it's like 29 now, right? L2 EVPN, EVPN, L2 VPN, VPLS, VPN v4, VPN v6. Like the list goes on and on and on and on and on, right? And so always confirm and with your customers, what are all the services you're running? And can you give me, and then start verifying the amount of entries in all those address families. The last thing I wanted to talk to you about was detecting and, when an event occurs, when the CPU goes high. So you can use EAM scripts. I mean, this is a solution from the 1990s, right? Now, you guys must have seen this, but there are more obviously sophisticated solutions now with NXOS, IOSXR. These are containerized boxes, bash shell. You can use scripting. You can do, it's an open platform, right? So whichever way you want to, interface with the system to detect its state change, you can do it now, right? There's documentations on these things. If you look at the XR or NXOS telemetry operations guide, they're available on CCO. They'll give you examples of how you can pull that information from the system and then you write your scripts around it, right? But I just wanted to give you an example that if you wanted to detect any sort of sudden spike in CPU, you have more, automated event-driven ways to do that. This is a classic way of doing it from 20, 30 years ago, but nowadays I would encourage you guys to look at your automation teams, talk to them, and look at NXOS, IOSXC, and IOSXR. We have containers, we have, open telemetry systems that you can just pull any state information from the system and write your own Python scripts, your bash shell scripts to address these issues. So that is all I had. Does anyone have any questions? I just have 2 minutes left. And this time I was on time. Last time I exceeded 10 minutes. Yes, sir.
So the command maximum path IBGP whatever.
Yeah.
So how does it install the routing table? If it's C, let's say I have like 8 paths.
Yeah.
So will it install all the 8 paths from my OSP?
No. They have specific criteria. I don't know it from the top of my head, but you have the first things like the weight should be the same. It should be coming from the same AS and all that. And then based on those conditions, then it will be installed. Now, if you're doing unequal cost path load balancing, then you need things like add path and BGP pick. That's a different solution. But yeah, I don't remember from the top of my head, but the fundamental answer is that there is a criteria. If those criteria are met, then it installs it. But they have to be equal cost. Those criteria are to define equal cost, yeah. Any other questions? Yes, sir. Oh, by the way, I have a slide on that, but I skipped it because I know it's going to become a big conversation. All right, but it's a very good question, and if you have 5 minutes, we can talk about it. All right, so slow period detection, let's explain what happens first. First of all, we have a group of NAT routers that have the same outbound policy, okay? And what I mean by outbound policy, let's assume that we have 15 routers, right? They're neighbors with me. I'm the local router. And I've applied the same outbound route map. What the router will then do is place them in the same update group. And why do we do that? We do that because we don't want to send our BGP update through the same filter 15 times and send it to these same 15 neighbors. Why don't we just choose one neighbor, which is we call the leader. We call one of the 50 neighbors the leader, and I will apply that outbound policy, right, and then send it to the leader. Then after that, the result of that outbound policy, I'll replicate to all the remaining 14, right? So then what happens is that one of the other routers, not the leader, may be very slow, right? Because remember, the leader is the first one I updated, so the leader's table version number is increasing over time first, right? Now the other remaining 14 are getting the updates. Now that one of those routers is very slow in receiving the update, and that's why we call it the slow peer. Then what happens that router is so slow, right? That router is so slow that now, one thing I forgot to tell you is that as I'm sending an update for my outbound updates, I have one single cache that I use, right, to generate these updates. And because of that slow router, what happens is that my cache, and remember, network is dynamic, right? The network is dynamic. State changes are happening. I'm having to generate more updates. So what happens over time is that slow peers router's queue fills up. That slow peers router's queue fills up, and then it actually drags the update for the leader also, eventually, because my cache fills up. So how do we deal with that? We remove that router. It depends on the platform. Again, it's very platform specific. XR will take care of that for you. iOS XR will take care of that for you by default. It will move that slow peer to a different update group so the other 14 don't suffer. Right? In iOS, our solution is move this, put a dummy outbound policy towards the slow peer so that it moves to a different update group and it doesn't slow the rest down. Right? So it's all very platform specific. But yeah, slow peers, one thing that you can do, maybe this is a transient issue. You could clear what we call the TCP socket session with that slow peer, and maybe it may clear out the queue, and then the peer may come up. Maybe during that time, that router's CPU was very high, it was low on memory, right? The system cleared out, then it starts to send the update again. That's a way that you can try to mitigate the issue also. Yes?
So BFD for BGP, do you recommend it, or what advantage it has? Will it solve the slow peer problem, or
BFD? No, BFD will not have any influence or relation to slow peer, but BFD is just maybe the only place that it can have. Let's look at this scenario, right? It depends on the situation. So if I have a directly connected iBGP peer, right, like directly physically connected, and the interface goes down, immediately the system will detect that, right? Immediately. I mean, the carrier delay may be 100 milliseconds or whatever, right? But even if you do 0, immediately the routing protocol will know that my peer is down because the connected interface is down. Now you may be in a situation where there's a switch in the middle, right? Some transport device in the middle. Then the eBGP neighbor is there. Then you could probably use BFD, right? Then you have iBGP peering, right? Multi-hop iBGP, right? Or multi-hop eBGP. You could do BFD also for that. But there's something else called next hop tracking, right? Next hop tracking depends on your IGP, which is pretty good. So what does it do? My next hop to get to a particular network, the BGP keeps track of that. And if your ISIS and OSPF is designed well, the convergence is quite fast. But again, it won't be as fast as BFD. Yeah. You have multi-hop also. Yep. Okay. Any other questions? All good? So, yeah, I hope this 45 minutes was worth it. We only talked about one thing, updates, but that's all I could do. All right, take care. Have fun.